so first let me say I'm super excited to be here. Thank you for giving me the opportunity to talk. It's wonderful to see so many friendly faces, people I haven't seen in a long time, as well, so many new faces. I am humbled by the quality of the talk, especially from students. You guys are amazing. What I wanted to talk today about was the work of, is the work of a former student of mine, Tyler Houston. Tyler was an ASTRO 3D honors student in 2021. The years go by so fast. He was did his honors with myself and Manadeep Sina. Just to say as well, the reason why I'm giving this talk and not Tyler is that last year he went on to work in a high-paid industry job, which was wonderful for him. But he decided that he loved research, wanted to go back, but not astronomy. So sorry to us. He's currently, he's just started a PhD in Germany doing climate science. So ASTRO 3D and the students are having impacts, not just in astronomy, but the broader physical sciences. And I think that's great. Okay, so we have seen, whoa, we've got lots of green buttons here. There we go. Sorry, I'd invite you all up to have a look at this if I had time. There we go. All right, so we've seen this a lot of times. I don't want to dwell on it because you all know what the star-forming main sequence is. Now, I just want to point out, this is such a fundamental plot in physics, right? So you remember your equations of motion that you learned in first year physics, right? Remember the position velocity diagram. Right? It's a property and the time derivative of a property, velocity, right? This is littered throughout physics, right? It's everywhere. And this is one example in astronomy. It's the mass and the time derivative of the mass. So it's not surprising that we use it. It features all the time in extragalactic astronomy. We use it all the time. So we're going to use it in this talk, right? And what we're going to try and understand are this population of red and dead or quiescent galaxies. Okay, so we're going to use this star-forming main sequence to try and understand this population. So we've already seen in this talk and throughout the talks that there's a number of ways that you can quench or kill off star formation in galaxies. You know, that it's usually revolves around some kind of feedback. Okay, and so we'll have some AGN feedback or supernova feedback. These are very different physical processes and they happen at different mass scales, but quite often, as far as the galaxy is concerned, the end result is the same, that it shuts down star formation. So I just want to point that out because it will become relevant at the end. So Tyler comes into my office in the start of 2021, sits down, I think probably almost everyone here is either an honors student or has been an honors student. So do you remember that moment you sat down with your supervisor, you're talking about your project, what am I going to do? So, you know, we were talking about, and I say to Tyler, you know, there's like 3 things that I kind of really want to know. And so maybe you can help me answer these questions. I kind of broadly know the answers to these questions, but I want numbers. We can get numbers. So here's the first thing. I want to know how much of a galaxy's life is spent in quiescence, not forming stars, right? How much is it? Like a number, I don't know, right? I didn't know, right? I know that, you know, big galaxies, by the time they get to redshift 1, shut down, blah, 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 right? But can we get a number? Okay, so how many times does a galaxy that's on the star-forming main sequence, its normal place to be, fall off the main sequence, go quiescent, and then jump back on, right? How often does that happen for a galaxy, say, as a function of its mass? And when it's off the main sequence, how long does it stay off before it comes back on, if it comes back on at all? Like, what's the number, right? Or the numbers for different mass scales. Like, oh, we should be able to answer this, okay? So Tyler, go for it, right? And so that's what he did. So Tyler being awesome. So Kara, are you here? No, not here. Complaining profusely yesterday about we need all these multi-wavelength observations. We need to know the histories of galaxies. We can't know that. I wanted to jump up and say, hang on. We do know that. We can know that. We have these things called simulations, right? Now, a little asterisk, not the real universe, but, you know, let's forget that for the moment. Let's just apply our best theoretical simulation. This is, by the way, the Uchu simulation. It's, for those who know their simulations, it's 12,800 cubed. 2 trillion particles, one of the largest n-body simulations ever run, might have been eclipsed now, but as of a few years ago, absolutely massive, right? Billions of dark matter halos at redshift 0, which means that we can put billions of galaxies in there. So massive data set, right? So we didn't use all of Uchu in this project, just a tiny fraction. We didn't need to, right? So here we go. So what Tyler did was he got the model, the galaxy formation model, the SAGE galaxy formation model. Manadeep made him a catalog, 50 outputs, so the entire history, and he followed every single galaxy from their birth all the way down to redshift 0. And at each point in time, he worked out where the star-forming main sequence was in the simulation. Okay, and he tracked how each galaxy moved relative to the main sequence at each redshift, how often it went off and back on, and counted, right, these numbers, these questions that we want to answer. All right, so there's a real problem here, though. How do you define the star-forming main sequence, though? So for observers, it's actually pretty easy. Normally, you just have a snapshot. You have galaxies here, and so you have this idea of what it means to be quiescent. So you define that, and you say any galaxy that satisfies that is quiescent off the main sequence, and the rest, you know, on the main sequence, or maybe they're above bursting or something like that. But we need a consistent definition that tracks all the way back through, because we're following galaxies from their birth, maybe, you know, at redshift 15 or whatever, all the way through their history. And so Denari came up with a good way to do this. And so it's, you know, it's quite simple and transparent. You divide your galaxies at each redshift up into mass bins, and then you work out the median of that mass bin, and you say anything that's lower than 1 sigma off that median, we're going to define as off the main sequence. That's our quiescent galaxies, our quenched galaxies. Otherwise, they're on the main sequence. Okay. And so this is a very simple, transparent way to do things, and you can apply it at any redshift because the main sequence moves as a function of redshift. So it's consistent across all of cosmic time. The nice thing is, see this blue line here, this is the typical definition we use at redshift 0, a specific star formation rate of -11. All right, and that's according to this. So with Tyler has using this definition, that's the black and the red points. The red points are the quiescent galaxies, and you can see that it lines up nicely with the classic redshift 0 definition of being red and dead. So, you know, everything is pretty consistent with the way it's defined by observers, but it's consistent across all the outputs of our simulation, so we can apply it at all times. So awesome. So Tyler's tracked every single galaxy, knows where they are relative to the main sequence, calculates these numbers. Great. Back into my office, Tyler comes. All right. Question 1, Tyler, how much of a galaxy's life is spent in quiescence? Let's do this broken into mass spins. Here's the answer. Here I'm showing the fraction of its life, of its entire life. The dots in the back are just sort of a random sampling, just in the binning, so you can see the variance, but the variance is also captured in the bars. But just focus on the data points here. We can see that the fractional time in quiescence is highest at low and high masses, and it's a minimum in between. And so those numbers that I said, it's typically about 45%, about half, especially at low mass for low mass galaxies, but it drops to about 7% for Milky Way type galaxies. Okay, so we sort of know this. This is an inverse of, you know, where star formation efficiency is maximized. It's, you know, at the Milky Way scale. So this highlights that. All right, Tyler, question number 2. How many times will a galaxy jump off the main sequence and perhaps jump back up? Here we go. There, right? The number of periods that a galaxy jumps off the main sequence. Again, broken into mass spins. So low mass galaxies are much more likely to fall off the main sequence into this quiescent phase than higher mass galaxies. You can kind of see here that, you know, these points, low mass, are higher, than it sort of plateaus down. You can see the variance goes up here for very massive galaxies. What's happening here is our massive galaxy population is really a mix of these red and dead massive elliptical quenched galaxies and very large star-forming spiral galaxies. So that might be a problem with the model. Even remember, these are galaxy formation model results, or something interesting to look at, but that's what it is in the data. Typically 2.8 times. If you're a low mass galaxy, you're going to fall off the main sequence, come back up on average, compared to less than 1, you know, 0.7 times. All right, question 3, Tyler. What is the average time a galaxy is quiescent when it falls off the main sequence? And here is that answer. Here's the length of periods. You see, this is up. Whoa. This is up to gigayears here. We probably could have zoomed in a bit lower to see the features, but basically for low mass galaxies, they're really only off the main sequence for very short periods of time, less than a gigayear, but the high mass galaxies, potentially much longer. But you can see here, there's quite large scatter in the different kinds of galaxies once you get up above the Milky Way scale into groups and clusters, and that's exactly what we expect. Now, we quantified all this in this paper that we published earlier this year in Monthly Notices, letter. And so here are all the numbers. These were the numbers I asked how they produce. So we actually gave numbers and the error bars, the variances around it. So it's wonderful. If you're ever curious about these numbers or you need it for your own results, please go have a look at this paper. But let me just sort of give you the story here. So what's the story, right? The total average time in quiescence is largest for high and low mass galaxies. And it's smaller, it's minimized for the Milky Way type galaxies. So that's not controversial, but it's different. The reasons are different and the behavior is different for low and high mass galaxy populations. For low mass galaxies, they move in and out of quiescence frequently, although it's typically only for short periods of time. And we can tie this back to the effects of supernova feedback. It's very stochastic. They go off, right? Off the main sequence they go. They create some more gas, back onto the main sequence they go. So it's a very stochastic process, but for the high mass population, it's quite different. Our high mass galaxies, they actually spend a little less time in quiescence on average, but this is really just due to the mix of very high mass star forming galaxies and very big red and dead elliptical galaxies. So when they're quiescent though, they're quiescent basically permanently. And this is the AGN feedback, the radio mode feedback that shuts down star formation in these galaxies. And with that, I would like everyone, because we're about to go to coffee break, to put your hand up in the air like this. Go, everyone. Come on, Lars. Thank you. All right. And I will take questions.